Every single week, a single large-scale vermiculture operation can produce over 40 tons of vermicompost, the nutrient-rich organic fertilizer that earthworms create by consuming organic waste. In just 1 year, a commercial worm farm with 10 million earthworms can process more than 2,000 tons of agricultural waste, transforming materials that would otherwise end up in landfills into premium soil amendments worth hundreds of thousands of dollars. How do farmers breed and maintain massive colonies of earthworms that work around the clock, converting garbage into garden gold? What industrial systems allow these operations to harvest, process, and package millions of pounds of vermicompost while maintaining the living worm populations that make it all possible? And why are American farmers, gardeners, and agricultural entrepreneurs increasingly turning to vermiculture as both a profitable business and a solution to our most pressing environmental challenges? Welcome to AgriCraft, where we explore the innovations transforming American agriculture from the soil up. Today we are diving deep into the fascinating world of commercial earthworm farming, revealing the breeding techniques, feeding strategies, and harvesting technologies that make large-scale vermiculture possible. From selecting the most productive worm species and creating perfect living conditions in thousands of cultivation beds, through automated screening systems that separate finished compost from living worms, into quality inspection protocols and packaging lines that prepare products for distribution nationwide, we will show you every step of this remarkable biological manufacturing process. All will be revealed in this video. Earthworms have been nature's original recyclers for hundreds of millions of years, breaking down dead plant material and returning nutrients to the soil long before humans walked the earth. However, the deliberate cultivation of earthworms for agricultural purposes is a relatively recent development in the long history of farming. Ancient civilizations recognized that earthworm-rich soils were more fertile, but they did not understand the mechanisms behind this observation or attempt to farm the worms themselves. Cleopatra of Egypt declared earthworms sacred and forbade their removal from the land, recognizing their essential role in maintaining Nile Valley fertility. Aristotle called earthworms the intestines of the earth, an apt description of their role in processing organic matter. However, systematic vermiculture as we know it today began only in the 20th century when researchers started investigating the science behind earthworm biology and their remarkable ability to transform waste into fertility. The modern vermiculture industry took off in the United States during the 1970s and 1980s, when environmental awareness was rising and organic farming was gaining momentum. Pioneers like Mary Applehoff, who wrote the influential book Worms Eat My Garbage, helped popularize the practice for home composters and small-scale farmers. By the 1990s, entrepreneurs recognized the commercial potential and began scaling up operations, developing the industrial techniques that now allow farms to manage millions of worms and produce vermicompost by the ton. Today, the United States vermiculture industry generates over $150 million annually through the sale of live worms, vermicompost, and liquid worm castings. The market continues growing rapidly as organic farming expands, regenerative agriculture gains mainstream acceptance, and municipalities search for solutions to organic waste management challenges. Commercial vermiculture operations now exist in nearly every state, with concentrations in California, Florida, North Carolina, and the Pacific Northwest, where climate conditions and agricultural markets create ideal business environments. International comparisons reveal significant differences in vermiculture scale and focus. India has embraced vermiculture extensively, with government programs promoting small-scale operations for rural farmers seeking low-cost organic fertilizers. China operates some of the world's largest industrial vermiculture facilities, processing municipal organic waste in cities with populations exceeding 10 million people. European countries, particularly Italy and Spain, have developed sophisticated vermiculture industries focused on high-value specialty products for organic vineyards and vegetable production. However, the United States leads in agricultural technology innovation, developing automated systems and quality control standards that are setting new benchmarks for the global industry. One surprising fact that shocks even agricultural professionals is that earthworms can consume their own body weight in organic matter every single day under optimal conditions. A mature red wiggler worm weighing approximately half a gram will eat half a gram of food material daily, converting roughly 60% of that material into nutrient-rich castings, while using the remaining 40% for energy and growth. When you scale this biological factory to populations of millions of worms, the processing capacity becomes truly industrial, rivaling mechanical composting systems at a fraction of the energy cost and with superior end products. The foundation of successful vermiculture begins with selecting the right earthworm species for commercial production. Not all earthworms are created equal when it comes to farming. The common earthworms found in garden soils and agricultural fields are generally poor candidates for intensive vermiculture because they require deep soil burrows and cannot thrive in the shallow bed systems used in commercial operations. Instead, vermiculture farms rely on specialized species that naturally inhabit the surface litter layer of forests and grasslands. The undisputed champion of commercial vermiculture is Eisenia fetida, commonly called the red wiggler or tiger worm. These small reddish worms with distinctive yellow bands thrive in organic-rich environments and reproduce incredibly quickly under proper management. A single red wiggler can produce 2 to 3 cocoons weekly, with each cocoon containing 2 to 20 baby worms that mature in just 60 to 90 days. This reproductive rate means populations can double every 60 to 90 days under optimal conditions, allowing farmers to rapidly expand breeding stock or recover from harvesting. Red wigglers tolerate the crowded conditions of commercial beds far better than other species. While soil-dwelling earthworms require significant personal space, red wigglers happily live at densities exceeding 1,000 worms per square foot of bed surface. This tolerance for crowding is essential for commercial viability, allowing operations to maintain massive populations in relatively compact facilities. The worms also handle disturbance and harvesting stress much better than sensitive species, remaining productive even when beds are regularly worked and materials removed. Another commercially important species is Eisenia hortensis, known as the European nightcrawler. These larger worms grow to 4 or 5 inches in length compared to the 2 to 3 inch red wigglers, making them popular for fishing bait markets. European nightcrawlers also produce excellent vermicompost, though their slower reproduction rates and lower tolerance for crowding make them less efficient for operations focused purely on compost production. Many commercial farms maintain separate populations of both species, selling red wigglers primarily to other vermiculture operations and gardeners, while marketing European nightcrawlers to fishing suppliers and bait shops. Some specialized operations work with Perionix excavatus, the Indian blue worm, particularly in warmer climates. These tropical worms process organic matter even faster than red wigglers and thrive at temperatures that would stress temperate species. However, they are more sensitive to temperature fluctuations and handling stress, making them challenging for mainstream commercial production. Research continues on other species and hybrid breeding programs, seeking to develop superworms that combine the best traits of multiple species. Environmental requirements for earthworm cultivation are specific but manageable with proper facility design. Temperature represents the most critical factor affecting worm health and productivity. Red wigglers function best between 55 and 77 degrees Fahrenheit, with optimal performance in the 65 to 72 degree range. Temperatures below 40 degrees cause worms to become dormant, while temperatures above 85 degrees create potentially lethal stress. Commercial facilities in regions with temperature extremes require climate control systems, though many operators use simple insulation and shading rather than expensive heating and cooling equipment. Moisture management is equally critical because earthworms breathe through their skin and require consistent moisture to survive. Bedding materials in cultivation beds should feel like a wrung-out sponge, damp throughout but without freestanding water. Too dry and worms cannot respire properly, becoming stressed and eventually dying. Too wet and oxygen levels in the bedding drop, creating anaerobic conditions that suffocate worms and promote harmful bacteria. Commercial operations use moisture meters to monitor beds and install simple irrigation systems that can add water during dry periods, while drainage systems prevent waterlogging during wet weather. Oxygen availability matters because earthworms are aerobic organisms requiring constant airflow through bedding materials. Properly prepared bedding maintains air spaces between particles, even when moist, allowing oxygen diffusion to depths where worms feed and live. Commercial farmers use fluffy materials like shredded paper, cardboard, coconut coir, or peat moss as bedding bases, all of which maintain good structure and resist compaction. Regular turning or mixing of beds introduces fresh air and prevents the anaerobic zones that would kill worms and create foul odors. The pH level of bedding materials affects both worm health and microbial activity essential for decomposition. Earthworms prefer pH ranges between 6 and 8, slightly acidic to neutral conditions that support robust populations of beneficial bacteria and fungi. Materials that are too acidic, below 5.5, irritate worm skin and inhibit beneficial microbes. Highly alkaline conditions above 8.5 create similarly hostile environments. Commercial operations test pH regularly and amend bedding with agricultural lime to raise pH or sulfur to lower it, maintaining optimal conditions as organic matter decomposition naturally acidifies bedding over time. Starting a commercial vermiculture operation requires establishing robust breeding populations through careful stock selection and nurturing. Many new farmers purchase starter colonies from established operations, acquiring proven genetics and benefiting from the seller's experience in maintaining healthy populations. A typical starter colony for a small commercial operation might include 20,000 to 50,000 adult red wigglers, enough breeding stock to establish productive beds and begin expansion. These founding populations receive premium care in specially prepared nursery beds designed to accelerate reproduction. Farmers create rich bedding mixtures, combining multiple materials for optimal texture and fertility. Shredded cardboard provides carbon and maintains structure. Aged manure or compost supplies nutrients and beneficial microbes. Coconut coir retains moisture while resisting compaction. The resulting blend creates an ideal environment where worms focus energy on reproduction rather than merely surviving. Feeding strategies during the establishment phase emphasize high-quality materials that support reproduction without creating problems. Overfeeding young colonies can backfire, causing uneaten food to decompose anaerobically and create toxic conditions. Experienced farmers start conservatively, offering small amounts of feed and increasing gradually as populations expand and consumption capacity grows. Preferred feeds during establishment include pre-composted vegetable scraps, coffee grounds, crushed eggshells, and thoroughly aged animal manures that will not heat up or introduce pathogens. Early care includes vigilant monitoring for problems that could devastate young colonies before they become established. Farmers inspect beds multiple times weekly, checking moisture levels, observing worm behavior, and watching for signs of pests or diseases. Healthy worms appear plump and active, quickly burrowing away from light when beds are opened. Sluggish worms or mass migrations from beds signal environmental problems requiring immediate intervention. Cocoon production serves as a key indicator of colony health, with abundant cocoons throughout the bedding, confirming that conditions support reproduction. As populations grow, farmers expand operations by splitting colonies and establishing new beds. The doubling time for red wiggler populations under optimal management ranges from 60 to 90 days, allowing aggressive expansion when market conditions justify it. A farm starting with 50,000 worms can realistically grow to over 1 million worms within a year, through careful management and reinvestment of reproductive output into new breeding beds, rather than sales. The cultivation phase represents the heart of commercial vermiculture operations, where earthworms transform organic waste streams into valuable products. Modern farms use various bed systems depending on scale, climate, and available materials. Outdoor windrow systems arrange bedding and worms in long, low mounds that workers can access from both sides. These windrows typically measure 4 to 6 feet wide and 2 to 3 feet tall, dimensions that maintain proper moisture and temperature while allowing air penetration. Windrow systems work well in mild climates and suit operations processing large volumes of agricultural waste. Indoor bin systems use stacked containers or flow-through reactors that provide better environmental control and higher production per square foot of floor space. Flow-through systems represent the cutting edge of commercial vermiculture technology. These vertical reactors continuously harvest finished vermicompost from the bottom, while fresh bedding and feed are added at the top. Worms naturally migrate upward toward food sources, leaving their castings behind. This continuous production eliminates the boom and bust cycles of batch systems, providing steady output that matches market demand and simplifies inventory management. Feeding represents the most labor-intensive aspect of vermiculture and the key determinant of production rates and product quality. Commercial operations source organic feedstocks from diverse suppliers, often arranging to collect materials that would otherwise require expensive disposal. Food processing facilities provide fruit and vegetable trimmings. Coffee roasters supply spent grounds. Breweries offer spent grain, and livestock operations provide manure. This waste-to-product model creates revenue from multiple streams, including tipping fees paid by waste generators, compost sales, and live worm sales. Feed preparation is essential because earthworms lack teeth and can only consume materials softened by bacterial and fungal decomposition. Many commercial operations pre-compost feedstocks in dedicated areas where materials undergo initial decomposition for 2 to 4 weeks before worm exposure. This pre-processing accomplishes several goals. First, it allows potentially dangerous heating to occur before worms contact materials. Fresh manures and vegetable waste can heat to temperatures exceeding 160 degrees during initial decomposition, levels that would kill earthworms instantly. Second, pre-composting reduces material volume through moisture loss and decomposition, concentrating nutrients and extending the working life of bedding materials. Third, it allows volatile compounds like ammonia from manure or acids from citrus waste to dissipate, preventing chemical burns to worm skin. Feeding frequency and quantity require balancing maximum production against overfeeding risks. Underfeeding reduces output and allows worms to consume bedding materials meant to provide structure, leading to compaction and oxygen depletion. Overfeeding creates anaerobic pockets that suffocate worms and generate offensive odors that create neighbor complaints and regulatory problems. Experienced farmers develop feeding rhythms matched to their specific operations, often applying feed weekly or bi-weekly in layers across bed surfaces. Watching how quickly worms consume previous feedings guides future application rates, creating a feedback loop that optimizes productivity. The harvest stage in vermiculture involves separating finished vermicompost from living earthworms, a process that presents unique challenges given that both products occupy the same space and the worms are mobile, living creatures. Timing the harvest requires judging when sufficient castings have accumulated to justify the labor and equipment costs of processing, while ensuring enough breeding stock remains to restart production. Most commercial operations harvest beds every 3 to 6 months depending on feeding rates and bed systems used. Manual harvesting methods work well for small operations but become impractical at commercial scales. The simplest technique exploits earthworm photophobia, their aversion to light. Farmers dump bed contents onto tarps under bright lights or direct sunlight. Worms immediately burrow toward the center of the pile to escape light, allowing workers to scrape away outer layers of finished castings. Repeating this process gradually reduces the pile until only a dense ball of worms remains, which returns to beds for continued breeding. This method works but requires significant labor and stresses worms through repeated light exposure and handling. Mechanical harvesting systems revolutionize commercial vermiculture by processing material quickly while minimizing worm stress and labor costs. The most common system uses vibrating screens with mesh sizes selected to pass finished castings while retaining worms and unprocessed organic matter. Material from harvest beds feeds onto conveyor belts carrying it to the screening machines. The screens vibrate at specific frequencies that encourage worms to ball up or move away from screen surfaces, improving separation efficiency. Finished castings pass through the mesh and collect in bins or bags below, while worms and larger particles remain on screen surfaces and discharge into collection containers for return to active beds. More sophisticated operations use multi-stage screening with progressively finer meshes that separate materials into distinct size fractions. The first coarse screen removes large unprocessed debris and the majority of worms. Intermediate screens capture partially processed material that returns to beds for additional worm processing. Fine screens produce premium finished castings with particles smaller than an 1/8 inch, the consistency preferred for potting mixes and top dressing applications. This grading process creates multiple product grades serving different markets and price points. Automated systems in the largest operations integrate screening with conveyors, sorting equipment, and packaging lines in continuous processing plants reminiscent of food processing facilities. Materials flow from harvest beds through a series of industrial machines that clean, screen, grade, and package products with minimal human contact. Computerized controls monitor flow rates, adjust machine speeds, and track production volumes. These systems can process multiple tons of material per hour, achieving economies of scale that make large operations competitive with industrial composting facilities, while producing superior end products. Quality control in vermicompost production ensures consistent properties that meet customer expectations and organic certification standards. Visual inspection remains important despite automation. Trained workers examine processed castings for worm eggs, baby worms, and unprocessed debris that should not appear in finished products. The presence of cocoons in premium grades indicates inadequate screening, while large worms in castings suggest process failures. The smell provides important quality information. Properly finished vermicompost has an earthy forest floor aroma. Sour or putrid odors indicate anaerobic decomposition and inferior products that can harm plants rather than help them. Laboratory testing provides objective measurements of physical and chemical properties. Moisture content testing ensures castings fall within target ranges. Typically 30 to 40% moisture for bagged products. Too dry and castings become dusty and difficult to re-wet. Too moist and they become heavy, expensive to ship, and prone to anaerobic conditions during storage. Nutrient analysis quantifies nitrogen, phosphorus, potassium, and micronutrient concentrations, allowing accurate label claims and helping customers make informed purchasing decisions. The best operations test every production batch, building databases that track quality over time and reveal trends suggesting process adjustments. Microbial testing verifies the biological richness that makes vermicompost superior to conventional composts. Beneficial bacteria and fungi populations should number in the billions per gram of castings. These microorganisms contribute to disease suppression, nutrient cycling, and soil structure improvement when castings are applied to gardens and fields. Some operations also test for pathogens including E. coli, salmonella, and parasites that could present human health risks, particularly for products marketed for vegetable gardens. The thermophilic phase of pre-composting should eliminate pathogens, but testing provides verification and liability protection. Heavy metal testing ensures products meet organic certification standards and do not contain contaminants from industrial waste streams. Even when sourcing materials carefully, unexpected contamination can occur. Regular testing protects both producers and customers, catching problems before products reach markets. Reputable operations maintain detailed records showing test results for every batch, creating traceability that satisfies organic certifiers and discriminating customers. Processing beyond basic screening adds value and creates specialized products for different market segments. Some operations produce liquid extracts by steeping finished castings in water, creating concentrated solutions rich in soluble nutrients and beneficial microbes. These worm teas serve foliar feeding applications and soil drenching, offering convenient liquid alternatives to solid castings. Producers must manage extraction carefully to prevent anaerobic conditions that breed pathogens rather than beneficial organisms. Aeration during extraction and proper storage prevents problems. Pelletizing transforms loose castings into uniform granules easier to handle, measure, and apply with standard fertilizer spreaders. Industrial pellet mills compress moist castings through dies, creating cylindrical pellets that dry into hard, dust-free products. Pelletized vermicompost commands premium prices from professional landscapers and turf managers who value ease of application and consistent results. The processing equipment represents significant capital investment but creates product differentiation in competitive markets. Blending allows producers to create custom formulations combining vermicompost with other organic materials. Products might include castings blended with peat moss or coconut coir for potting mixes, combinations with rock minerals for complete organic fertilizers, or mixtures with biochar for enhanced soil carbon storage. These value-added products serve specialized niches and generate higher margins than commodity castings. Packaging and distribution systems must preserve the living biological properties that make vermicompost valuable while enabling efficient handling and attractive retail presentation. Unlike synthetic fertilizers that remain stable indefinitely, vermicompost is a living product containing billions of organisms that require moisture and air to survive. Packaging must balance protection during shipping against the needs of the living contents. Breathable bags constructed from woven polypropylene or burlap allow air exchange while containing products. These materials prevent the moisture buildup that occurs in sealed plastic bags, moisture that quickly creates anaerobic conditions, killing beneficial microbes. For retail products, operations use attractive printed bags with clear windows, showing product quality and detailed information about application rates, benefits, and the production process. Effective packaging becomes a marketing tool that educates customers and justifies premium pricing compared to conventional composts and fertilizers. Bulk products for commercial customers ship in super sacks, 1-ton capacity woven bags that forklifts and front-end loaders easily handle. These industrial packages minimize handling labor for large-scale users, including farms, golf courses, and municipal landscaping departments. Some operations offer bulk truck delivery, blowing castings directly into customer storage areas or spreading them immediately onto fields using specialized application equipment. Labeling meets regulatory requirements while communicating value propositions to customers. All bags must display guaranteed analysis stating minimum nutrient concentrations for nitrogen, phosphorus, and potassium, along with manufacturer contact information and net weight. Many producers include detailed application instructions, crop-specific recommendations, and information about the environmental benefits and sustainable production methods. Some operations include QR codes linking to videos, demonstrating proper use and explaining vermiculture science. Storage of finished products requires climate-controlled facilities that maintain viable microbial populations until products reach end users. Moderate temperatures between 50 and 75 degrees prevent excessive heating or freezing that would harm or kill beneficial organisms. Adequate ventilation prevents moisture accumulation and anaerobic conditions. Most operations aim to minimize storage time, producing to order when possible, and maintaining inventory levels that balance demand variability against the costs of warehousing and the risks of product deterioration. Distribution channels connect vermicompost producers with diverse customer segments spanning hobby gardeners to commercial farms. Direct retail sales through farm stores and websites serve home gardeners seeking premium organic products and willing to pay prices reflecting quality and production methods. These customers value detailed information, customer service, and the story behind products, often becoming brand advocates who spread word-of-mouth recommendations. Garden centers and nurseries represent important wholesale customers purchasing products for resale. These businesses seek reliable suppliers providing consistent quality, attractive packaging, and reasonable wholesale pricing that allows retail markups. Successful producers develop strong relationships with retail partners, providing point-of-sale materials, staff training, and promotional support that moves products off shelves. Landscape and lawn care professionals purchase bulk quantities for installation and maintenance projects. These customers prioritize performance and ease of application over packaging aesthetics. They need products that deliver visible results quickly, as their reputations depend on healthy, attractive landscapes. Building relationships with landscape professionals requires demonstrating product effectiveness through field trials and providing technical support for application questions. Organic farmers and market gardeners represent a growing segment seeking alternatives to synthetic fertilizers and soil amendments. These agricultural customers make purchasing decisions based on cost per acre, nutrient analysis, and documented yield improvements. Producers serving this market must understand agronomic needs and speak the language of farming, demonstrating how vermicompost fits into comprehensive fertility programs. Some operations offer soil testing services and customized application recommendations, providing value beyond the product itself. Shipping logistics challenge vermicompost distributors because products are relatively low value per pound compared to shipping costs. Weight-based shipping charges quickly eliminate profitability for distant customers. Successful operations build regional customer bases where ground shipping remains economical. Some establish relationships with freight consolidators and common carriers, negotiating volume discounts that improve competitiveness. For distant markets, producers focus on high-value products like concentrated extracts and pelletized formulations, where shipping represents smaller percentages of total delivered cost. Byproducts and secondary revenue streams improve the overall economics of vermiculture operations. Live worms themselves represent valuable products serving multiple markets beyond vermicompost production. Red wigglers sell to new vermiculture operations seeking breeding stock, home composters setting up worm bins, and educational programs using worms for teaching environmental science. European night crawlers serve bait markets, with fishing supply stores and online retailers purchasing thousands of worms weekly during fishing seasons. Prices for quality worms typically range from $20 to $35 per pound, substantially higher than vermicompost pricing. Worm cocoons command even higher prices in specialized markets. Serious vermiculture operators purchasing breeding stock prefer cocoons over adult worms because cocoons ship more easily, suffer less stress, and allow buyers to raise worms adapted to their specific systems from hatching. A single cocoon sells for 10 to 50 cents depending on species and seller reputation, making cocoon production potentially more profitable than vermicompost for operations focusing on this niche. Educational programs and farm tours generate revenue while building public awareness and goodwill. Many vermiculture operations host school groups, master gardener workshops, and farm tours teaching sustainable agriculture and waste reduction. These programs charge modest fees while creating opportunities to sell products directly to engaged audiences. Some operators offer consulting services, helping others establish vermiculture operations, sharing hard-won knowledge for fees that supplement production income. Environmental impact and sustainability represent core value propositions, distinguishing vermiculture from synthetic fertilizer production and conventional composting. Vermicompost production requires virtually no fossil fuel inputs beyond transportation and minimal electricity for screening and packaging equipment. The earthworms themselves provide the processing power, working around the clock without fuel, lubricants, or spare parts. This biological manufacturing process stands in stark contrast to synthetic fertilizer production, which requires high temperatures, pressures, and energy inputs that generate substantial greenhouse gas emissions. Vermiculture diverts organic waste from landfills, where decomposition under anaerobic conditions generates methane, a greenhouse gas more than 25 times more potent than carbon dioxide over a century timescale. By processing food scraps, agricultural waste, and manure aerobically through earthworm digestion, vermiculture operations prevent methane formation while creating products that rebuild soil, organic matter, and sequester carbon. Life cycle analyses show vermicompost production creates net negative greenhouse gas emissions when waste diversion benefits are included, making it one of the few agricultural processes that actively fights climate change. Water quality protection represents another significant environmental benefit. Conventional fertilizers frequently leach into groundwater and surface waters, creating pollution problems including toxic algae blooms and dead zones where oxygen depletion kills aquatic life. Vermicompost releases nutrients slowly as plants need them, with binding to soil particles preventing leaching. Research shows vermicompost applications can reduce fertilizer runoff by 70% or more compared to equivalent nutrient inputs from synthetic sources. Soil health improvements from vermicompost extend beyond simple fertility. The diverse microbial communities in quality castings recolonize degraded soils, restoring biological functions lost through decades of intensive agriculture. These microbes form symbiotic relationships with plant roots, improving nutrient uptake efficiency and triggering plant immune responses that reduce pest and disease problems. Long-term vermicompost use rebuilds soil structure, increasing water infiltration and storage capacity that makes farms more resilient to both droughts and floods. From selecting the remarkably productive red wiggler species and creating optimal environments where populations can double every 60 to 90 days, through feeding strategies that transform thousands of tons of organic waste into valuable resources, to automated screening systems and quality control protocols, ensuring consistent, premium products, commercial vermiculture represents biological manufacturing at its most elegant. These operations prove that the most powerful agricultural technologies are sometimes the smallest, with earthworms no bigger than your finger, creating fertility that industrial chemical plants cannot match. The future of American agriculture increasingly recognizes that soil health forms the foundation of sustainable, productive farming systems. As organic acreage expands, regenerative practices gain adoption, and environmental concerns shape agricultural policy. Demand for vermicompost and the biological soil health it delivers will only grow. The vermiculture operations scaling up today are positioning themselves at the forefront of an agricultural revolution that works with nature rather than against it. Thank you for watching this journey through the fascinating world of commercial vermiculture, where earthworms transform waste into wealth and biology becomes technology. If you found this exploration of organic farming and soil regeneration interesting, please give this video a thumbs up and subscribe to AgriCraft for more deep dives into sustainable agriculture and agri-entrepreneurship. Leave a comment below telling us about your experiences with composting or vermiculture, or suggest other agricultural innovations you would like us to cover. Until next time, keep exploring the incredible organisms and practices growing our sustainable future.